welcome to this video. This is entitled D4.2 Faraday's Law. Those numbers come from the IB syllabus, and this is an HL topic. However, if you're studying any kind of Key Stage 5 or high school science, this would be appropriate for you. We're going to talk today about the effects of changing magnetic fields on EMFs, and then do some calculations using a really important law, which is Faraday's Law. As ever, my hope is that the videos are short, so please do pause whenever you are watching if you need to digest or take some notes, okay, and ask any questions you have underneath the video. I'm very happy to answer them. So let's get to it. Okay, induction is a term which is hopefully familiar to some of us, and we're talking today about Faraday's law of induction. Let's see an example of induction on the screen. Electromagnetic induction is the process whereby we are able to generate current, or more specifically an EMF, in a coil of wire by changing the magnetic field around that wire. Now you can see one way of doing that on the screen. We've got a magnet moving in, and as it moves out and in, we generate an EMF. We notice a couple of things. It's an alternating EMF. Sometimes it's positive, sometimes it's negative, and it's changing its magnitude all the time. Now, there's quite a lot going on here, and when we learn it at, say, GCSE, we talk about the idea of cutting field lines. As the magnet moves in and out, we're cutting across field lines, and that's generating the EMF. Today, we're going to try and make that a bit more of a mathematical process. And this links to the idea of a previous video, the idea of magnetic flux. Now, you may have wondered why we were learning about magnetic flux. Here's the reason why. Let's look at Faraday's law of induction. Faraday tells us that if we want to induce an EMF across a conducting coil or a wire, then what we need to do is change the magnetic flux through that coil. The exact wording we use is that the EMF induced is directly proportional to the rate of change of magnetic flux. Okay, so this is, I was going to say this is Faraday's law of induction. It's probably not. It's probably not how he wrote it originally. However, it's a modern version of it. Okay, and we can write it down in the following way. EMF is proportional to n, the number of turns, times delta phi over delta t. Phi here being the flux through one coil, and delta t being the time taken for that to do so. Now, it's sort of the case that over time this equation has evolved, and actually we sort of use it slightly differently. That proportionality sign implies that there's a constant that we don't have, but actually we've kind of modernized it just to say this. It's actually the two things are equal. Okay, in other words, the faster that this magnet moves, the higher the EMF we're going to get, or the slower it moves, the lower the EMF we're going to get. So really, we're interested in the ideas of change. Okay, this happens quite a lot in physics. Changes are the important bit. You think about forces, for example. In this case, if we can change the EMF, change the flux, sorry, then we can produce an EMF. Now, I think it's worthwhile sort of reminding ourselves how we calculate flux and what factors could be involved here. I've just substituted our flux calculation from the previous video into this one here. We've got n, okay, and then we've got a delta, and we've got a whole bunch of things which could change here. We've got B, the magnetic field strength. So what we could do is change the magnetic field strength. That's what's happening in the little GIF you can see on the screen. We're moving that magnet in and out, and therefore B is changing because we're changing the distance, and therefore we're going to get an EMF induced. Another thing we might want to do is change the area. We might have a constant field in a different area, and then we could also change the angle. This is quite a big one when we're looking at AC generators, and that's something that we'll be talking about in a future session. Okay, so if you're okay with that and you've taken notes, you've added the equation, you're kind of comfortable, let's try one example just to see how we get on with this. Okay, let's try this one. We've got a coil which has 3,400 turns and an area of 1 centimeter squared, and it's in a uniform field of strength, 0.4 Tesla. What's the average EMF if it's taken out of the field in 0.2 seconds? Actually, in terms of a calculation, this is fairly straightforward. It's not one which you need to worry too much about. We could think about a few things here. What is it that's changing? N is staying the same. The field strength is uniform, so it's staying the same. And actually here it's the area that's changing. Really what we're doing is we're going to pull it out of the field. So the amount of area of field which is being occupied by that coil is going to change. It's going to go from 1 centimeter squared to 0 because we're going to pull it out of the field and there's no field within the coil at that point. If you think you know how to do it, feel free to have a go. If you're not sure, then watch on just to see the explanation. Okay, let's go for it. So we're going to use our equation. We've got our EMF is equal to delta phi over delta t. Okay. Whoops, I've just realized there's a double n there. My bad. Okay. There should only be one n on the top here. My apologies. Okay, we've got our n, and as I say, we've got BA cos theta. Here we're going to assume that theta is equal to 0. Okay, where our field is just acting right through the coil. We know n is 3,400. We know b is 0.4. We know the time. And then we just need to do a little bit of a conversion here, which is to take that area from 1 centimeter squared into meters squared. Well, 1 centimeter squared, that's 10 to the minus 2 squared. That's 10 to the minus 4. We're going to divide that by the time, 0.2 seconds, and we're going to get an EMF of 0.68 volts. Now notice here, this is an average EMF. As you'll have spotted in the original slide, those EMFs change magnitude all the time. So all we can do right now is calculate averages without using a bit of calculus, which we can see in the next few sessions. We're unable to get instantaneous values. This is simply the average value of the EMF induced when we pulled it out of the field. Okay, that's enough from me just now. What we'll do in a future session is look at how this applies, as I say, to the generation of AC signals. Thank you very much for watching.